Alright, this is Unit 8, Lesson 2 of our calculus class. Unit 8 is called Differential Equations and Slope Fields. Lesson 2 is called Differential Equations, Round 2. What we're going to learn in this lesson is more complicated diffie-qs. We're still going to do algebraic manipulation, and that's going to be it for our diffie-q for this course. This is included in our class because there's going to be some need to know how to do this on the AP test, and then it'll set you up for some fun future calculus stuff. So here's a little more complicated one than last lesson. We have the derivative equation is equal to x plus 1 over e to the power of 3y plus 9. And so here's our derivative equation. To find the antiderivative, we're going to algebraically manipulate this thing so all the y's are on the left, all the x's are on the right, and then we're going to integrate each side. We're integrating the left with respect to y, we're integrating the right with respect to x. If you notice, the left side is going to be a u substitution. We have a function composition. We have a 3y plus 9 is the inner function, e to the power of x is the outer function, or e to the power of y in this case. So I'm going to say my u is equal to 3y plus 9. du would be 3 dy. And since we don't have a 3 here, we're going to end up with a 1/3 in our integral. And so I kind of just did that u substitution in my head. Like I wrote out the u and the du in green, but otherwise I did the u substitution in my head. If you want to work that out by a piece of paper to check my math, by all means do that. But anyways, so we're going to integrate this thing. We do have a u substitution there. The integral is going to be 1/3 e to the power of 3y plus 9. The right side is just a straight up power rule in reverse, so it's 1/2 x squared plus x, and then again plus c. We don't need to put plus c on both sides, we'll just put it on one. To find c, I'm going to pick out our initial condition. So 2, -3 is a point on our original function. So -3 goes in for y, 2 goes in for each x, and we're going to find out that c is equal to -11 over 3. Now, I'm going to plug in, take plus c out and put -11 over 3 into our equation. To solve for y, we have to do a little bit of log properties. So first I'm going to multiply everything through by 3. And then if e to the power of 3y plus 9 equals all this stuff in terms of x, I want to get that y out of the exponent. So I'm going to rewrite this exponential equation as a log equation. So the natural log of all this stuff in terms of x would be equal to 3y plus 9. And now to solve for y, I'm going to subtract 9 from both sides and then divide both sides by 3. So here's our function in terms of y. Or solve for y, I guess it would be in terms of x. Anyways, this is how you do this differential equation. We integrated it to find our set of equations that would solve this thing. And with our initial condition, we pinpointed the exact equation. Yeah. Another example, and there's really nothing special about this other example, other than the fact that we're using different pre-calc equations. And so we have a trig equation going on in here. We have a natural log we're going to get when we integrate the y side. So it is good to know some of these things. Like we have a u substitution again for the y's, and so we're going to get 1 over u, which is the absolute value, or which if I integrate 1 over u is going to be the natural log of the absolute value of u. So if I plug in our u back in, we get this right here. I know that the derivative of tangent is secant squared, so the integral of secant squared, or the antiderivative of secant squared, will just be tangent. And then we'll slap on our plus c. We have an initial condition. Pi over 4, 0 is on our original function curve. So I'm going to plug in pi over 4 for x and 0 for y, and we can solve for c. I'm going to stress this one. If you don't know that tangent of pi over 4 is equal to 1, that should be like one that you could easily figure out in your head. So if you're struggling with that, please let me know. I'll be throwing more trig practice at you in the next 2 weeks until we get up to the AP test. Heck, I'll probably even throw more in after the AP test, just because doing trig is like eating your vegetables. If you're going to do university math, it's just good to know your trig. And I'm sorry I said heck in a video for a class. Now I said it twice. Let's move on. So if we solve this thing for y, we're going to get a natural log and a tangent function. Tangent function we're just going to isolate and leave it there. The natural log, because the y is inside of that natural log function, we're actually going to turn that natural log, we're going to solve for the natural log, and then turn that natural log into an exponential equation. So now the x is inside of a function and the y is not, which is great because we want to solve for y. So I have, if I multiply both sides by -3, and then I change the log equation to an exponential equation, I get 1 minus 3y is equal to e to the power of -3 times tangent of x minus 1. And I can distribute that -3 to get -3 tangent of x plus 3. And then if I rearrange our terms here, I can get 1 minus e to this business is equal to 3y. Divide everything through by 3, and then I have solved for y. Alright, so that is a couple examples of more complicated differential equations. We've got a third one. Let's try this one out. Set the y's to the left, x's to the right. Integrate each side. We get this equation plus c. Our initial condition says that -2 is a point on our original function curve. So I'll plug in -2 for each of the x's and the y's. We'll find that our c is 1/2. So here's our here's our original equation. We'll solve this for y. Pretty straightforward. Alright, and so here's some more differential equation stuff that we can do. And again, if this kind of stuff is great stuff to write on a piece of paper and leave on your kitchen counter for your parents or older siblings to find, just to let them know how smart you are, in case they forgot. Boom.